Okay, let me once again remind you. So what is the positional system of representation of numbers? So for example, we have a number, something like that in decimal representation, right? So what does it mean? So you can just number positions. So here you have what you're probably used to call decimal point, but now we will call it radix. So essentially the point which separates integer and fractional part, right? So let us number positions. So it means that, okay, the number in the position 2, 1, has to be multiplied by 10 to the power 2, plus number in the position 1, 2, has to be multiplied by 10 to the power 1, plus number in this position 3 has to be multiplied by 10 to the 0th power, and plus 4 in the position -1 has to be multiplied by 10 to the -1, plus 5 in the position -2, 10 to the -2, and 6 in the position -3 has to be multiplied by 10 to the -3, right? So this, if you would collect together this and separately that, we would get that this is nothing else but 100 plus 20 plus 3, right? 123 plus 0.4 plus 0.05 plus 0.006. So these together will give us 0.456, right? So, but as we have seen on the last lecture, you can use different bases for representation of numbers. So for example, let us use base 2. And then, for example, if we have a number like that, in binary representation, we just perform exactly the same. So, so what does it mean, the base? So here we use base 10. It means that in every position, we can use one of the 10 characters, right? So these are the characters we use, which we use 2, 3, 4, 5, 6, 7, 8, 9, and 0, right? 10 characters, right? So in every position, we can have one of the 10 characters. So for binary representation, the only characters we can use is 0 and 1, right? So how many characters? 2. So this is why it's base 2, right? So here we do exactly the same. We just number our positions. And then it's just using exactly the same. So here, 1 multiplied by base, which is 2 in this case, 2 to the power 3, plus 0 multiplied by 2 to the power 2, plus, okay, let me separate it, plus 1 multiplied by 2 to the power 1, plus 1 multiplied by 2 to the power 0. So pay attention. This 0 is that, this one is that, and this one is that, right? Plus, here we have 0 multiplied by 2 to the power -1 plus 1 multiplied by 2 to the -2 plus, and so on, plus 1 multiplied by 2 to the -3, and here we have plus 1 multiplied by 2 to the -4, right? So as a result, how can we represent it? We can represent it in the following form. So essentially, you see what this point or radix separates. It separates integer part, which means positive powers of our base, right? And fractional part, which means negative powers of our base, right? So, okay, so how can we represent it? So this is 8 plus 0 plus 2 plus 1. So altogether, this will give us 11, right? Plus fractional part. So it's here 0, here 1 multiplied by 1 over 2 to the power 2. So it will be 1/4 plus 1/8 plus 1/16. So please, I leave it up to you how to convert it. So I believe you can add them. Okay, let me be not so lazy, so I will do this. 1/16 plus 2/16 plus 1/16. So it will be altogether 7/16. That's it. So this is fractional part of this binary representation number. Okay, so we used exactly this in order to convert numbers from decimal representation to binary representation. For example, let us consider a number 53.7. Okay, in decimal representation. So in order to convert it to the binary form, we just separate integer and fractional parts. So, for example, 53. First, we consider integer part, 53. So you know that it will be nothing else in the binary representation, but some 1 or 0 multiplied by 2 to some power, right? So this is what we do then. So we essentially divide by 2, and we are getting that this is 26 and the remainder is 1, right? So what it means, when we divide by 2, we essentially so move the last digit in the binary representation. So let us do it like that. So it has something there, and then it has 1, for example, right? And here, so it's integer part, integer. So then I know that it's 1 or 0 multiplied by 2 to the 0's power, right? So, and I know that if I will divide it by 2, so what will happen? It's like when we take the decimal number like that, for example, right? And divide it by 10. What happens? So if we divide by 10, for example, 123 divide by 10, so we are getting 12.3. So essentially what happens, the radix, which was here, is moving to the next by one position, right? So here, because we have base 2, so when we divide by 2, exactly the same thing happens. So if we had radix here, so when we divide by 2, we move it to the next position. So this is why when we divide by 2, the fractional part, the remainder of division by 2, is nothing else but the first digit of our number. Okay, so then we take these 26 divided by 2. So move it here. So the radix further when we divide by 2, right? So we are getting 13 and the remainder is 0. It means that here we had 0. So, okay. Now 13 divided by 2, it's 6 and the remainder is 1. So it means that, so when we divided by 2, we moved radix even further. So it means that here we had 1 because we have this, right? So 6 divided by 2, move radix even further. So we are getting 3, remainder is 0. So it means that here we had 0. So 3 divided by 2, so we are getting 1, remainder is 1. So we moved radix even further. So we got 1 here, right? And obviously 1 divided by 2 will give us 0, right? I mean, we should just stop here because everything else, what we will have will be just 0. So we cannot go further. So we don't have, we will get just zeros when we will be dividing by 2 afterwards, right? So that's it. So idea is exactly the following as if I would be using, for example, 123. So if you divide by 10, you will get 12.3. So this is the first number in the first position, right? Then you use 12 divided by 10, you are getting 1.2. So this is the number in the second position here. So you're essentially moving radix first here, then fractional part will give you exactly the number in the first position. Then when you divide by 10, your fractional part gives you the number in the second position. And then when you divide by 10 even more, moving the radix, so you're getting the number in the last position. So that's it. So essentially 1 divided by 10, 0.1. So this is your last number. Okay. So the same happens. Yeah. Really sorry. I should. Oops. This one. So that's it. This is where we stop. So it will give us 1 here. Okay. So I know that 53 in a decimal representation is nothing else but 1, 1, 0, 1, 0, 1. So in the binary representation, base 2. So I did it on the last lecture, and I even checked it, so you can check that it will give you 53 exactly. Okay, perfect. Now, because I want to convert this number 53.7, so I need to work with fractional part. So because it's fractional part, right? So I know that there will be radix in front, so like something like that. And so for example, b -1, b -2, and so on, right? So essentially it will look like that. b -1, either 1 or 0, multiplied by 2 to the -1, right? Plus b -2 multiplied by 2 to the -2, plus b -3 in the position here, b -3. So by 2 to the -3 plus and so on, right? All possible further negative powers of 2. Okay, so could you tell me how can we get this? So which is either 0 or 1. So how can we get it? What would you recommend? What will happen if I will multiply the whole number by 2? So I had b -1, b -2, b -3, b -4, and so on, right? So once again, because this is a binary representation, right? So we have base 2. It's exactly what we have in our decimal representation. For example, let us suppose that I have 1, 2, 3, okay, 5, right? So decimal representation, it means that it's 1 multiplied by 10 to the -1 plus 2 multiplied by 10 to the -2. So -1 position, -2, -3, -4, plus 3 multiplied by 10 to the -3, plus 5 multiplied by 10 to the -4, right? So how to get these, for example? If I multiply the whole number by 10, right, for the base 10 number, so 0 point multiplied by 10 will give me 1.235, right? So these, I can get this number as integer part, right, as a result. So the same happens here. So if I will multiply it by 2, so binary representation, so what will happen? The radix will move here. It's exactly like when we divide by the base of the representation, right? The radix moves to the left, one position. If we multiply, so it moves to the right on one position. So this is what I will get. So, and now integer part will be exactly my first digit of the representation, right? So I separated it from the fractional part. So we take our 0.7 and multiply by 2. We are getting 1.4, right? So integer part is exactly our b -1. So the first digit, okay, let me start writing it, 1. Okay, after that, I take the remainder. So like here, so this is the remainder, right? In this case, after I multiplied by 2, the fractional part. So I take 0.4, multiply by 2, I'm getting 0.8. So this is exactly this. So what I did, I moved my radix 1 position to the right when I multiplied by 2. So it means that I have 0 here. So 0.8 multiplied by 2, 1.6. So I moved my radix even further here. So this is b negative 2, this is b negative 3. So, okay. So fractional part 0.6 multiplied by 2, 1.2. So this is nothing else but b negative 4, right? Next, we take this 0.2 multiplied by 2, we're getting 0.4. So this is nothing else but our b negative 5. So 1, 0, 0, 0. But after that, this is what you get. Right? So every multiplication by 2 moved radix to the right by 1 position. And integer part is nothing else but exactly your b negative 1, so digits of the binary representation. Okay, so could you tell me what I will be getting further? Does it remind you anything? Hello?
Want to just repeat since...
Exactly, because you see, from here I will get 0.8 multiplied by 2 and so on, right? So it will repeat itself, right? Exactly. So I will be getting 1. So here. So this part, and it will be repeating itself. So I will be getting 0, 1, 1, 0, 0, 1, 1, 0, and so on infinitely, right? So this is binary representation. Okay, so I can write it. So usually we denote it like that: 0, 1, 1, 0, repeating infinitely. So this line separating infinitely repeating part of the fraction, so really denotes that it will repeat infinitely, right? So once again, I just showed you, so by using this, that this is an infinitely repeating part, but we will use just line on top. Okay. Now, after that, I can say that 53.7 in a decimal representation is nothing else but these one, one, zero, one, zero. Sorry, one radix, one, zero, one, one, zero, infinitely repeating in binary representation. So why it's so important? Why I just showing you all these conversions and so on? You could say that, okay, I don't care how it is represented in the computer, but this is essentially the most important part why we were doing this, because you can see that even such simple. So what is the fractional part here? It's that, right? It's just 0.7. So you see, it's a finite fractional part in decimal representation, but it is infinite fractional part in binary representation. As you understand, your computers are finite, right? So you have finite amount of memory in your computer. So it means that even when you will be representing the number, such simple number as, I mean, relatively simple example as 53.7. So in your computer, you will not be able to represent it exactly. You will be able to represent it only with some finite precision. Is it clear or not? Because you cannot represent this infinitely repeating zero with you cannot have in your computer infinitely repeating zeros and ones. So yeah, by the way, one elementary digit, so of binary representation, which is either 0 or 1, it's called bit. So a set of 8 bits, so and here you have, let's say, 1 0 0 1 0 1 1 1, right? So 8 bits is called 1 byte. So altogether, so okay, then have you ever heard, probably you heard that amount of memory is computed in your cell phone is computed in gigabytes, right? So this is essentially, I mean, not exactly, but almost. So kilobyte or kibibyte. So now it's agreed that this is just 1,000 bytes, and what is called kibibyte is 1,024 bytes. So where 1,024 comes from? Because it's 2 to the power 10. So it's just convenient to compute if you're talking about binary representation to use powers of 10. So essentially, 1,000 of kilobytes will give you megabyte, and so 1 megabyte is 10 to the 6 bytes. and 1 megabyte is so some time ago people were using only these powers, but then recently standardization institutes agreed that, okay, we want to separate this and that. So standard prefixes like kilo and mega, which we usually use, which are just means that you need to multiply the unit by 1,000, right, or by 1 million. So in order to separate them, so standard institutions started to use kibibyte and mebibyte instead of what was used before, kilobyte and megabyte. So also what happened that the companies which are producing, for example, hard drives or something like that, they were started cheating. So so although everybody, all the electronics professionals were using these definition, and they were calling these kilobyte before, but companies who were producing hard drives, they started saying that, okay, they were putting in fine print that 1 kilobyte for them is equal to 1,000 bytes. And if you, so it looks like a very small difference, right? But if you are talking about gigabytes, so difference is not that small already. So, and this is why Standardization Institute decided, okay, let us separate what was used before by computer professionals and what is used by everybody else. Okay, so now, so what is the most important result of what we just studied? We can see that even this number 0.7, right? So you cannot represent it exactly with any finite amount of memory, which can contain only zeros and ones. You cannot represent it exactly because you see it has infinitely repeating part. Okay, is it clear or not? So this part is infinitely repeating. So really, this number looks like, so I would need to write here this, and so on infinitely. So it means that even 0.7 you cannot represent exactly using any realistic computer. Okay, is it clear or not? Any questions? So you should understand this. Why? Because this will be, I promise you that in the midterm you would need to transform integer part, I mean some decimal representation number similar to that into binary representation. So I will ask you to do this. Any questions here? Okay, now when we are transforming binary representations to decimal, so I explain you that you just use something like that, right? So because it's positional system of representation of numbers, the only problems come when you need to transform infinitely repeating binary fractional part to the decimal number. For example, let us consider x, which is 0.1011, infinitely repeating in the binary representation. So how to transform it to the decimal representation? Okay, so this is how you do this. We use exactly the same rule what we used before. So when we multiply, so for example, let me consider, so 1 period, second period, third period, and so on, right? So I will use exactly the same property which we used before. So every multiplication by 2 moves radix to the right by 1 position, right? So for example, if I will multiply it by 2, this is what I will get. So pay attention, right? Okay. Now, if I will multiply by 2 more, once again, so I will move it here. If I will multiply by 2 once more, I will move it here. And if I multiply it by 2 once more, I will move it here. So essentially, x, so if I will move it 4 positions, so 1, 2, 3, 4 to the right, x multiplied by 2 to the 4th, I will get the following. So pay attention, infinitely repeating, right? Or you can write it as this, right? Is it clear what I'm doing or not? So now let me consider this and subtract x. Pay attention, this is nothing else but my original number x, right? So I know that this is they will cancel each other. And I know that this is nothing else but what? 0, 1, 2, 3, right? So 1 multiplied by 2 to the third, plus 0 multiplied by 2 to the second, plus 1 multiplied by 2 to the first, plus 1 multiplied by 2 to the 0th power. So I know that this is 8 plus 0 plus 2 plus 1, which is 11, right? Any questions? So as a result, I got the following equation. X multiplied by 2 to the 4th minus x equals to 11. So I can factor out x, 2 to the 4th minus 1 equals to 11. 2 to the 4th is 16. So I'm getting that x is nothing else but 11/15. So as a result, I know that 0.1011 in the binary representation is 11/15 in the decimal representation. Is it clear or not? Any questions here? Okay. Now, okay, so what to do if, so in this particular case, repeating part was starting right after the radix, right after the point, right? Separating the fractional part. Okay, if we have something like, for example, like that, let us start from this. Let me transform it to the decimal representation. So once again, if my x would, if the repeating part would start immediately after the fractional part, I would know what to do, right? But here, really, you're doing exactly the same thing. So you're just multiply by, for example, x, you can multiply by 2 to the second, so which would move radix 2 positions to the right, and you would get that it's binary, or you can say that this is 1,0 binary plus let us call this z, and this is nothing else but 2, right? So here, infinitely repeating part starts right after the radix. We know what to do with that, right? So could you tell me how to transform? So for example, if z is equal to 0.101 infinitely repeating binary, so how would you transform it to the fractional part, to the decimal representation of the fractional part? So what we need to do?
Would you start just by multiplying z by 2 to the third?
Yes, exactly, because essentially what I want to do, multiplying by 2 to the third, so I move radix 3 positions to the right, right? So I will get 101.101 and infinitely repeating, right? Or I can say that this is 101 binary plus but this is nothing else but my original z, right? Okay, let us transform 101 binary to the decimal representation. Okay, could you tell me, so this digit, what it gives us?
4?
What?
Oh, 1 times 2 squared, so 4.
Yeah. You're right that this is 4. I just wanted to do everything in all details. Okay, second digit, what it gives us?
0 times 2 to the first.
Yes. And these digits, what it gives us?
1 times 2 to the 0.
Right? So altogether, it's 4 plus 0 plus 1 equals to
5.
yes, thank you. So altogether, we are getting z multiplied by 2 to the third equals to 5 plus z, right? So which means that z multiplied by 2 to the third minus 1 equals to 5. So which means that, so 2 to the third is 8, right? Z equals to 5/7 in decimal representation, right? Okay, now just remember that we started from that, right? So we are getting that x multiplied by 2 to the second by 4 equals to 2 plus z, right? 5/7, right? So this is what is 2 plus 5/7? It's 19/7, right? So correspondingly from here, we are getting that x is equal to 19 divided by 28. Is it clear or not? Any questions? Okay, so as you probably understood already, that even to represent a relatively simple number 11, right? So we need already 4 digits in the binary representation. So it means that numbers in binary representations are pretty bulky, right? So you need to have a lot of digits. So this is why people use a little bit different representation. For example, let us consider number 1 0 1 1 0 1 0 0. So how many bits contains this number?
Maybe 8 bits.
Yes, exactly. So this is 1 byte, right? 8 bits correspond to 1 byte, right? So now what you can do with that, you can either split it in groups of 3 bits. 3 bits are not good here because you do not have enough numbers, but you can do this. You can just add 0 in front. Then you can do this. Or let me do it like that. Yeah. So, or you can split it into groups, the bits into groups of 4 bits. Okay. Could you tell me how many numbers you can represent using 1 bit?
2.
Exactly. 2 numbers, 0 and 1, right? Now, if I have 2 bits, how many numbers? So, for example, like that. How many numbers I can represent using 2 bits? So here I have 2 numbers, and here I have 2 numbers, right? And they are independent. It means that I need to multiply it. So I'm getting 4, right? You can also think about it in the following way. If you have a number, integer number using just 2 bits, so you have these, right? So the maximum number is 1, 1. Minimum number is 0, 0, right? So maximum number, so this is what? 2 plus 1, 3, right? And minimum number is 0. How many numbers I have between 0 and 3? I mean, not between, but how many numbers I can represent using 2 bits as a result? Okay, 0, 1, 2, 3, right? 4. So essentially, idea is the following: that every digit, 2 numbers, right? But then you separately can also represent 2 numbers with every next digit. So as a result, if you have, for example, 3 digits, so how many numbers you will be able to represent using 3 digits?
8 or 2 to the third.
Yes, thank you very much. So 8. What about 4 digits? Really 4 digits. So I don't need this. So with 4 digits, 2 to the 4th, right? 16 numbers. So essentially, idea is the following: that you can split your 8 bits in the byte. You want to split them into something which is, so we are used to decimal system, right? But 10 is not a power of 2, right? So this is why we need to convert our binary numbers using all this multiplication by powers of 2 and so on and so on. So as a result, instead of that, what you can do, you can split into digits, and then this number contains 4 bits, so you can represent by so these 4 bits can be can represent 16 numbers, right? And these 4 bits can represent 16 numbers, right? So as a result, you can use a number representation system with base 16. So it means that I need to have 16 characters, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I need new characters. So people use usually A, B, C, D, E, F. So 10 characters here. And 6 more characters here. So, for example, 1, 0, 1, 1 in a binary form, you can represent as 1 multiplied by, could you tell me, by what power?
2 to the third.
2 to the third plus
0 times 2 to the second.
plus
1 times 2 to the first. And plus 1 times 2 to the 0.
Thank you. So which would give me 8 plus 0 plus 2 plus 1. So 11 in decimal representation, but because here we use 16 chars already, right? So it will be A with the base 16 corresponds to 10, and then it's B in so it's called hexadecimal numbers. So representation with base 16. So okay, let me consider second part. It will be 0, 1, 0, 0 binary representation. It just 1 multiplied by 2 to the second equals to 4, right? So 1 byte I can represent as in hexadecimal representation, B4. Clear? Is it clear or not?
Yes.
Okay, so in some cases, people use so-called octal representation or octadecimal representation. So as you probably can figure out, so then you don't need these extra numbers, like I mean extra characters like in hexadecimal representation. You just use first 8 characters. 0, 1, 2, 3, 4, 5, 7. 5, 6, 7. Then, so essentially, for example, these. So three bits represent 8 you can represent 8 numbers starting from 0 to 7, right? So for example, these would mean 4, right? These 4 plus 2, 6, and this is 2, right? So you can say that this is 2, 6, 4 in octadecimal representation or octal. So just want you to know that. So I will not ask you to do this, to convert to octal representation, but I can ask you to convert some number to the hexadecimal representation. So so idea is the following, that you just take your binary number, split it into, if for hexadecimal, into groups of 4 bits, and every group will give you digit. And this is the next one, right? So this is the next digits in hexadecimal representation, and so on. So if you want to convert it to octal, so you see, for example, I had 8-bit, right? So you start from the right, separate 3-bit, then another 3 bits, and then because you don't have enough, so you can just add 0 here, so, and here another 3 bits. So is it clear or not how to do this? Any questions? So because you use groups of 3 bits here, for example, here, So this group of 3 bits is called triad. And if you use group of 4 bits, it's called tetrade. So from tetra and so on, so Greek words. So essentially, usually in most of the cases now, before people were using octal representation, octadecimal. So now it's relatively rare, and most of the time, if people want to represent some binary number in compact form, so people use hexadecimal representation. So or representation with base 16. Okay, so let us start next topic. And so we talked a little bit already how to convert fractional decimal number into binary form, but how these fractional numbers, or just any numbers, stored in our computer. Okay, let us consider so-called floating point representation. Of real numbers. Okay. So idea is the following. So for example, let me consider the following decimal number. So could you tell me, so this is normal, so just standard decimal number. Okay, let me do the following. If I'm not writing what base I'm using, so it will be decimal numbers, right? So I just don't want to write this stuff all the time. Brackets and 10. Okay. So probably you know that there is such thing as engineering representation. So which means that you bring the radix to the second position. This. So is it something you know? So I hope this is something you know. So it's representation of the number. So what is important that you know always that here you will have just one number, everything else. So radix is always in the second position. So, and then in order to compensate for moving the radix to the second position here, so you multiply by 10, which is base of your system of representation, positional system of representation of numbers, 10 to power 2. So you moved it to the left, radix to the left by 2 positions. So this is why you have 2, because when you multiply by 10 to the power 2, what will happen that your radix will be moved by 2 positions to the right? So, and you will reconstruct your original number. So this is exactly, so you can use exactly the same representation for example, this binary number. you can say that, okay, so this is integer number, right? So you have radix. You can say that you have radix here, but you can represent it as move it to this position. So how many times you need to do this? 1, 2, 3. Okay, 1, 2, 3, 4, 5, 6, 7. So you can write that this is 1, 0, 1, 1, 0, 1, 0, 0, multiplied in binary, multiplied by 2 to the 7th power, right? So it's analog of engineering representation just for the binary system. So what is interesting about the binary numbers? So if you have a decimal number, right? So, or you use 10 as a base of your representation, here number can be changing, right? So you can have here essentially any number, right? So if you are moving to, if you're using binary number, if you are moving radix to be to the right of the first non-zero digit, so then you know that your first digit is always 1, right? This one. So as a result, you don't need to store it. So all you need to store what goes after the radix, right? After that. So fractional part only. And you need to store the power of 2. So essentially, if you agree that you are storing a number like that, all you need to store is this, right? So you know that, okay, that it always has that in front, 1 and the radix, and you need to store, or if you like, you can write it like that. You need to store this power. So this and that only things you need to store. So, so if you know the power and if you know these numbers after decimal point, which are called mantissa, so you can reconstruct your original number. Is it clear or not? Any questions here? Okay, so really, of course, there is one more thing which you need to store. So because number can be positive or negative, right? So we need to store the sign. So here in this particular case, okay, it's 1, 0, 1, 1, 0, 0, 0, 2 to the 7th. So okay, we need just storage for these bits, right? 1, 2, 3, 4, 5, 6, 7, right? Then in order to store number 7, how many bits we need? Okay, what is 7 in binary representation?
It's 1, 1, 1.
Yes, it's 1, 1, 1 in binary. You can think about it if 1, 0, 0, 0 is 2 to the power 3 is 8, right? So minus 1, so you are getting just this, right? Okay. So we need 3 bits, right? And how many bits we need to store sign? So how many values can sign? Sign can take? It's only plus or minus, right? 2 values. So in order to store either plus or minus, how much bits we need?
Just 1.
Yep, 1 bit. So the result, in order to store this number, we need 11 bits, right? 7 bits to store the mantissa, and 3 bits to store the power, right, of 2, which is called exponent, and 1 bit to store the sign. Okay, so of course, you don't know in advance what number you would like to represent, right? So as a result, you just reserve some amount of memory, some number of bits for every part of the number. So for mantissa, for exponent, and for sign. So this is what differs. What differs different precisions of representation. So precision. And so we have single precision, double, long double, quadruple precision. So let's say like that. So only relatively recently I had to work with quadruple precision in my research. So okay, sign. Obviously for sign, you don't need more than 1 bit, right? Exponent. So single precision uses 7 bits. Double precision uses 11 bits. Long double 15. So let me limit myself by just these 3. And mantissa. So single precision uses 23 bits for mantissa. Double precision uses 52 bits for mantissa, and long double uses 64. So altogether, 1 plus 8 plus 23, so it's 23 plus 9, 32 bits, right? So here, 1 plus 11 plus 52 64 bits. And here, 16 plus 67 is, could you tell me? 83. Or here you can say that, so essentially, you see higher precision requires more storage, right? So this is 4 bytes, this is 8 bytes, and this is even more than 10 bytes. So inside of the floating point coprocessor, if you are working with double precision numbers, so this is what is used inside of the coprocessor, and just to avoid loss of precision, and then you're getting, as a result, output is 64 bytes. So, but it uses a little bit more bytes of precision to compute things inside without loss of precision.